Hello, and welcome to this session on gentle Bayesian updating with David Manley. I'm Habiba, and I'll be the MC for this session. We'll be starting with an 18-minute talk by David, then we'll move on to a live Q&A session where he'll respond to some of your questions. You can submit questions using the box to the right-hand side of this video. You can also vote for your favorite questions to push them higher up the list. Now I'd like to introduce our speaker for this session. David Manley is an associate professor of philosophy at the University of Michigan, Ann Arbor. He teaches at the graduate and undergraduate level on a wide range of areas in philosophy. Here's David.
I teach philosophy at the University of Michigan, and I'm going to provide a gentle introduction to Bayesian updating. Because effective altruism is obviously about doing good in a way that's backed up by evidence, we want to make sure that we can change our beliefs in a way that responds to the evidence. And so you've probably heard a lot about things like updating on evidence, about having priors, degrees of confidence, and so on. And so this is supposed to provide a non-technical introduction to the ideas behind the sort of Bayesian framework for dealing with evidence. And this is the required picture of me and as a student. This is me in grad school about 20 years ago. So I'm going to start with a simple example. It's sort of a baby toy example, and I'll be exaggerating the degree to which we have like very specific degrees of confidence just so we can do the math. But obviously we're more or less confident in things. We shift our degrees of confidence, but often they're not extremely specific. So let's say you think probably your friend's not home because it's noon on a Tuesday or something, and so you think she's probably out. And then you see that her light is on, and so you get evidence that she's home. And now the question is sort of, what do you do to sort of integrate that initial belief that she's not home with your new evidence? And we're not very good at doing this intuitively. There's lots of evidence from social psychology, cognitive psychology, that we do this really badly. So Kahneman and Tversky's work and so on. And just to give you an example, so let's suppose, maybe this is a statistical fact that she's only home at noon on a Tuesday 1 in 5 times, or maybe you just have roughly that degree of confidence to begin with. And then let's suppose she's 3 times more likely to leave the lights on if she's home than if she's not home. That's really all you need to get the degree of confidence you should have afterwards. But we're actually not very good at doing this intuitively. So, just looking at this, most people can't say, I have undergraduates who've taking calculus and all kinds of advanced math classes, but they can't do this, and they certainly can't do this in their heads. Those who know, like Bayes' theorem, will sometimes take out their pencils and write out the theorem and try to plug in numbers and so on. But it's fascinating because the math it looks like it should be extremely simple. Obviously, you can't just multiply a 1/5 by 3 because then it would be way too easy. And that would give you 3/5 probability that she's home, and that's too high. That would make it more likely than not that she's home, and in fact it's more likely than not that she's not home even after you get that piece of evidence. But getting at exactly the right degree of confidence here is slightly tricky. That's the whole idea. In my last talk, I talked about how it's really important to be able to separate out your prior degree of confidence from the strength of the evidence that you get. And we'll see why that matters here. So this is the theorem that I used to use. It tells me that my new degree of confidence in this hypothesis should be, this is a form of called Bayesian conditionalization, with the right-hand side is Bayes' theorem, so spelled out fully. But what's really interesting, if those of you who know these terms or have seen this equation, think about the fact that there are only a couple of terms in here. A probability of not H is derivable from the probability of H, and so you just really have these 3 things, and it's very annoying that you have to plug in all of this stuff. So even for those of you who know this, it might be nice to hear about a simpler way that you can actually just do this in your head. For those of you who don't understand any of this, that's totally fine too. All you really need to know are a few simple things. The first simple thing is what it is for something to be evidence in this framework is that actually just what it is for something to be evidence, let's be real, is that observation is more likely given the hypothesis than given that the hypothesis is false. So think about the lights case. If your friend's the kind of person who leaves her lights on all the time, then it's just not any evidence at all that her light lights are on. If your friend's the kind of person who literally only leaves her lights on when she's home, never leaves her lights on when she's not home, then it's great evidence, really strong evidence, conclusive evidence that she's home. If it's somewhere in the middle, then the evidence is not as strong. So really, that's all there is to know about whether something is evidence, and all there is to know about the strength of the evidence. So you may have heard of things like p-value, which is sort of a way of trying to evaluate the strength of evidence. But this comparison, the probability of the observation given the hypothesis, probability of the observation given the hypothesis is false. Compare those two things. How many times more likely is one than the other? That's called the Bayes factor. That actually is a stronger, more informative, richer way of evaluating the strength of evidence than anything else, including p-values. So, but just intuitively, it's not, forget about the notation and all that, just intuitively, it's just, consider this observation, and then consider, hypothetically, if the hypothesis were true, how likely is it the world would look like this? How likely is that I'd make this observation? If the hypothesis were false, would the world look like this? Would I make this observation? And compare those likelihoods. And that's the strength of the evidence. And notice, this is something that I emphasized in the previous talk, that has nothing to do with whether you think the hypothesis is probably true or false. Like you might think it's almost certainly false. The strength of the evidence, then you're going to have to integrate with the fact that you have reason to think it's false to begin with. But the strength of the evidence itself is totally independent. We just asked this hypothetical thing. Supposing H were true, how likely is it that I'd experience this observation? Supposing H were false, how likely is it that I would make this observation? That requires actually being able to set aside I called it in the last talk, decouple your prior confidence in H, and just assess those hypothetical things. All right, so we've already said that we know she's 3 times more likely, or we figure she's 3 times more likely to leave the lights on if she's home than if she's not home. And so the strength of the evidence is represented by 3. It's 3 times more likely, right? So the strength of 3, a Bayes factor of 3, or a strength factor, you might call it, of 3. And our prior confidence is 1/5. So we need to be able to integrate these two things. I've said it's not as simple as just multiplying one by the other. But, so all we need to do is a simple, there's one simple little hump that we need to get over, and that is to stop thinking in terms of fractions for our prior confidence, or probability, or chance, or whatever it is. Often our prior confidence is governed by something that we know about chance, or some statistical fact, or something like that. And we usually express these things in terms of fractions or in terms of percentages. But if we're going to do it this way, we need to stop doing that. We need to shift over into thinking it in terms of odds. Okay, so remember from 5th grade, odds are pretty straightforward. And then we're going to get this equation. So this is the master equation. This is, I showed you that big equation before, the Bayesian conditionalization with the right-hand side exploded using Bayes' theorem. This is all you need. Prior odds times the strength of the evidence, the strength factor, the Bayes factor, which we've already introduced, is our new odds. So now really all we have to do is convert our prior confidence into odds. Now, odds, easy, right? The probability of picking a banana at random from these fruits is 1 in 5. And so what that's representing is that fraction has the total, right, as the denominator. And instead of using the total as a denominator, what we're going to do is just look at this sort of relative ratio here, the banana, number of bananas compared to number of apples. So 1 to 4, for every 1 banana, there's 4 apples. And we just don't think about the total, right? We just think about the 2 groups. That's it. So that's odds. So the odds of picking a banana from this group is 1 to 4. So now, so we can convert. Before we said the probability of her being home on a Tuesday is 1 in 5. We're going to say, no, for every 1 day she's home, there's 4 days she's not home. The way we're representing it, the odds is 1 to 4. And now we can just multiply. What we're going to do is multiply the side of the odds that we got evidence for. This the 1 represents the side of the odds in which she's home, and the 4 represents the side of the odds in which she's not home on a Tuesday at noon. We're going to multiply the side that we're getting evidence for, which is the 1, right? That's the one that it's more likely that the lights are on if she's home. And just multiply that by the strength factor, we get the new odds. That's it. Our new odds, 3 to 4. And in fact, that means our, if you want to express it in terms of a fraction, our new degree of belief should be 3/7. So it's a little less than half, as I said before. So that's it. That's the whole thing. But we'll run through some other cases. Actually, first a little visual. This is like a little flowcharty thing. You know, start with a 1 to 4 odds, and then just multiply the side that you're getting evidence for by the strength factor, and then you end up with the 3 to 4 odds. Perfect. Okay. So this is just like a case with different numbers. Suppose in the background, you know that this disease affects 1 in 1,001 people, and you want to be tested. You know, it's not like there's more evidence. You don't have any symptoms or anything like that. You're just being screened. And the test itself is never wrong if you have the disease. So if you have it, it's definitely going to tell you that you have it. It won't tell you that you don't have it. No false positives for people who, no false negatives for people who don't have the disease. No false negatives for people who do have the disease. And then it's wrong 5% of the time if you don't have the disease. So, of the people who don't have the disease, 5% of them are going to have false positives. The people who do have the disease, they're all going to get positive tests. There aren't going to be any false negatives. All right. So that seems like a pretty good test. And if you ask most people, should I be now very worried that I have this disease? They say yes. And in fact, if you go to Harvard Medical School and you ask attending physicians and medical students and house staff what the probability is that the person has the disease after this test, and given the background fact that 1 in 1,001 people have the disease to begin with, you get a really interesting spread, right? You get the people who know how to do it, and they get the right answer about 2%, although some people make it even lower. But then you get a whole bunch of people just basically ignoring the base rate and doing something with that fact that it's wrong 5% of the time if you don't have it, and getting 95%. And so those people are going to really freak out their patients if those are the things that they know about the test, because the correct answer is about 2%. All right, but we can look at how we get that. So our prior confidence, 1 in 1,001. Convert that to odds, it's 1 to 1,000. That's convenient. Strength factor. Well, that's really easy in this case. The probability that I get a positive test if I did have it. Remember, we're setting aside, in order to evaluate the strength of the evidence, we set aside entirely how likely it is that we think the hypothesis is true. So this is a totally hypothetical assessment. If I have the disease, what's the probability that I get this positive test? The answer is 1, certainty. If 100%, that is. If I don't have the disease, what's the probability I get a positive test? Well, 5%. Okay, so it's a strength factor of 20. This is very strong evidence. And keep in mind, this is the kind of strength factor of 20 is the kind of evidence where in a lot of sciences, people will say that you can reject the null hypothesis, right? Like this is like really good evidence that you have the disease. And the problem is that's not enough, right? We got to integrate that with our prior odds. So prior odds 1 to 1,000, strength factor of 20, new odds of 20 to 1,000, which is still pretty low, right? That's 20 in 1,020, or 2 in 102, or 1 in 51. Very, pretty unlikely. So we can look at this using the flowchart again. 1 to 1,000, multiply the side of the side of the initial odds that you're getting evidence for, that is having the disease, multiply that by the strength factor that you got evidence for, 20 to 1,000. And let's look at it visually. Got 1,000 people who don't have the disease. You have 1 person who does have the disease in blue. You test everybody. The person who has the disease gets test positive. But 5% of the people who don't have the disease also test positive. So 50 out of 1,000 people, right, are also going to test positive. That's a lot of people who are testing positive. And it's just because there's so many people who don't have the disease, right? It is only 5% of them, but it's still a lot of people. And now that I've tested positive, I can actually just ignore everybody outside and zoom in on that sort of that area that's consistent with my evidence. So all I'm going to do is zoom in on the people who have the positive test, and I'm interested in the ratio of people who have the positive test who have the disease versus people who have the positive test who don't have the disease, and that's 1 to 50. So that's it. But you know, so you can do this sort of population method. In a lot of cases, you could like imagine. In the lights case, you could say there's a big population of Tuesdays, and you know, in a fifth of them, she's home, and then like think about how that integrates with the fact. But you know, often it's not that convenient, which is why just prior odds times strength factor equals new odds is often the easiest way to do it. So now I just want to introduce one more type of case. This is one where you don't have a statistical basis for your prior, you just have a kind of theoretical basis for the prior, but it's still really important. So suppose I say to you, I'm going to predict this 20-sided die roll with my ESP, and my ESP is perfect, I'm going to get it right. And then I say, and you know it's a fair die, you know, I use one of your dice. I say, you know, it's going to come up 14, and I roll, and it comes up 14, and then I leave. So there's no further way to sort of evaluate me. What should you think about whether I have ESP? Well, it's very strong evidence, right? Probability that I'd predict it if I had ESP, let's say about 1. Probability that I'd predict it if it were just chance, 5%, right? So it's a strength factor of 20. Again, this is the kind of strength that in a lot of studies will say, you know, I can now reject the null hypothesis. Can we reject the null hypothesis of chance? Absolutely not, right? I don't have ESP. How do you know? Well, there's really a lot to say about that, right? We have background knowledge about how the world works. We know a lot of people have had the opportunity to prove that they have ESP and they haven't. It'd be very weird if just this one person had ESP, sort of go against everything we know about physics. And so, you know, unless you kind of in the background already believe in this kind of phenomenon, you probably think it's very unlikely. And so there's lots of philosophical issues about how to think about theory choice and you know, desiderata of comparing theories to each other. But you have good reason to think that ESP doesn't exist. And you know, exactly what should your prior be? Well, it doesn't really matter that much, right? Maybe it's 1 to 1,000,000. If it's 1 to 1,000,000, you have a strength factor of 20. You're still not worrying very much. You're now at 1 to 50,000. And I'm going to have to actually guess a bunch of die rolls in a row before you're going to start to even really get worried. I need a strength factor of 1,000,000 to sort of get you, I'm very worried that I have ESP. So the point here is that this sort of Bayesian approach of considering, you know, having some prior and then considering the evidence doesn't just apply to cases like the disease case where you have some statistical background, some sort of base rate that's, you know, a matter of like counting up people. So it's not that, you know, well, 1 in 1,000,000 people have ESP, so what's the probability to have ESP in this case? It's a theoretical assessment. But, you know, whatever your degree of confidence was before getting the new evidence, this is how you should update. And I hope that's useful. I'll take some questions now. Thanks.
Thank you for that talk, David. We now have a few minutes for questions, so I'm just going to dive straight in with one from Quinn here in the chat. Do you have any recommendations for training, for example, books with exercise that people can practice this kind of skill?
Sure. Well, first, I should say that the book Reason Better will be available through that link that I provided for, as far as I know, 6 months at least. And people can always contact me if they need it, and it doesn't seem to be available. There's a great book online called Odds and Ends by Weisberg. There's another book by Ian Hacking called Intro to Probability and I think it's called Introduction to Probability and Inductive Logic. But oh yeah, Jonathan Weisberg is so Jonathan Weisberg has this free text online. It's really great. So odds and ends, I highly recommend that.
Nice, good recommendations. And another question from, okay, so diving into a bit more of the technical kind of issues around calculations. Our second top question is around taking into account second order uncertainty. So for example, your uncertainty about what the prior odds or the Bayes factor are. So is there a version of this calculation that you can use to take that into consideration?
This is a hard question. So among formal epistemologists, there's a disagreement about whether we should even represent this as anything other than just a kind of smearing of what we assign to the probabilities. So like the strength factor is the probability of evidence given the hypothesis over the probability of the evidence given the negation of the hypothesis. What does it mean to be uncertain about what those values are? Well, those values are supposed to represent our confidence to begin with. They're not supposed to represent some kind of objective like chance. So whatever it is, if you're uncertain about the chance, you're uncertain about some kind of objective probability fact or statistical fact, then that's supposed to be already built into the confidence that's represented by those values. There are, so I would say in philosophy, there's a lot of debate about whether we should think of these kinds of conditional probabilities as having some kind of objective answers, setting aside statistics or chance, and that what we're doing is like trying to get the right conditional probability, and those people who are more subjectivist about it who just say this is just your confidence. So I mean, one way to say it is we obviously will need to work with a version of this where we're thinking of something like a set as really being what the value is that we assign to these things. So it might be a range. So you can think of it as like smeared across. Instead of 1/5, for example, in our original story, it could be smeared across a bit of a range. And then there's a lot of technical work about exactly how that ought to be done. But then you can just imagine sort of imagine a bunch of individuals that in your brain, as it were, like a little committee, each of which has that view. And then imagine each of them updating, and then what you end up with is the range, the new committee after the update. So that's one kind of model for representing at least a kind of smeared distribution of your prior probabilities. It's not exactly the same thing as higher order uncertainty, but I can't. It's too technical to get into.
It sounds like we've hit upon, this questioner has hit upon a complex issue in epistemology.
Yeah, no, it's great though. There are some great questions in the neighborhood.
Okay, I guess another question from someone, any rule of thumb on how to set your priors? For example, in the ESP example, should it be 1 in a million or? Yeah,
well, luckily in a lot of these cases, I think it doesn't matter that much. So one thing that's really I think a fundamental issue in the philosophy of science, for example, is roughly when you have equal evidence between two hypotheses, are there any other criteria, desiderata, like simplicity, coherence, that sort of count, or beauty, maybe elegance or something like that, that by themselves ought to count as things that we consider to be more likely to be true. For some people think that's just a kind of practical matter, and some people think that actually simple theories are more likely to be true. But for it does look like what we in fact do, what scientists in fact do, for example, is to give more initial weight to theories that are more elegant, more simple, and so on. And there doesn't seem, nobody's really come up with a way of doing that in extremely. I mean, there are attempts, Kolmogorov simplicity, to try to formalize what it would be and figure out exactly what a prior might be on a range of theories that we don't haven't yet evaluated evidence for. But, you know, in these cases, we really have a lot of other facts. Like in the ESP case, I think what we're really going on is, even if you might have started off like as a baby, sort of 50-50 between ESP and not ESP, in fact, you've gone, you know, it doesn't really matter that much what your initial prior is. I think you've gotten enough evidence over the course of your life to sort of converge on a very low, you know, prior right now. So when I say prior, it's always prior relative to the new piece of evidence that you're coming up with. So it's the, but that doesn't mean that prior hasn't been informed by previous evidence. So yeah, I think like in the ESP case, I've gotten all kinds of evidence throughout my life that ESP doesn't exist. I don't know. Yeah, it'd be very hard to put a number on that, but probably because I haven't done a great job, you know, the whole time of properly updating in response to every
all the failed versions, all the failed.
Yeah, but I could try to start over and just ask myself, like, suppose I were 50-50, just given the way the world is, the fact that so many people have had the ability to try to demonstrate the existence of their ESP if they could, and so on and so forth. Like, what is the, you know, and given what I know about human psychology, our ability to sort of fall into thinking that things are strange and weird when really they're just unlikely, and so on. It just looks exactly like a world where ESP doesn't exist, given that. And yeah, but I don't know.
Okay. Okay. Well, that is unfortunately, I guess we'll have to leave it there. That is unfortunately our time. But David is going to, I think, have a go at answering the top-rated question in the chat afterwards around how he's personally used this kind of gentle Bayesian and updating.
All right. Sorry. Okay,
well, thank you so much, David, and thank you everyone for watching. Before you leave the session, please do give us your feedback in the poll section of the live chat. Thank you.
All right.